Hello, everyone. I'm Yuan Luo from iKang Healthcare Group. Today, our presentation's title is Empowering Provision Healthcare with Apache Airflow. Pretty much, we want to share with you how we use Apache Airflow to build iKang's DataHub. In this presentation, we want to give you a quick introduction about iKang first, and then share with you how we use Airflow within iKang. As everyone knows, healthcare's data isn't just big, it's messy, multimodal, and time-critical. Today, we're going to share with you how we use Airflow to turn that chaos into reliable, clinical useful workflows. Why this matters? Workflows that is reliable, observable, and compliant is actually a clinical requirement, not a luxury in healthcare industry. So we want to start with you why we chose Airflow, and then zoom into event-driven patterns that we use to automate radiology and health report generations. First, let's give you a quick introduction about iKang. On the right side, that's iKang's branding metrics. Within the inner circle, that's the three main health checkup brands within iKang. In the outer circle, on the right side, we have iKang dental care services. We have outpatient services. We have like Medifast, that's the services within Hong Kong. We also have dedicated services for women and children. On the left top part, that's the string APP's logos. We use that as the online platform to serve our customers better online. iKang has been established for 20 years. By 2024, we serve about 10 million customers every year. And in the last 20 years, we have also accumulated about 80 million healthcare data within iKang. This is a high-level architecture overview of iKang's data tech stack. As you can see, we integrate both batch and streaming under one unified lakehouse architecture and use Airflow as an orchestration engine for full lifecycle data governance and real-time analytics across all the clinical operations. That's including the pipelines from HL7 or FHIR messages, or leads, packs, or lab results, and doctor's notes. We chose Airflow because first, it's easy to integrate with some other systems. Second, it's flexible enough for clinical scenarios, like branching, retries, SLAs, immediacy. All these features can fit into different clinical scenarios. Third, we could adopt it with minimum code changes to different systems and different teams. One takeaway, Airflow is the orchestration backbone that lets multiple clinical systems to work and move safely and in order. More specifically, we already leverage the platform to support many critical workflows in different scenarios. First is the typical usage as the data ingestion. No matter it's HL7 FHIR REST interface to the message box, or it's data records from PACS read systems, we use Airflow as the ingestion engine. The data actually has been used to support clinical decisions and real-time monitoring and alerting. That's also including multimodal data monitoring and analytics. The data ranging actually from structured database records, lab result, to unstructured data like the images, physician's notes. We can see two kind of unique data challenges in healthcare. First is the multidimensional data. Medical data usually involves intricate semantic relationships, such as linking the structured lab indicators with unstructured physician's reports, no matter it's ultrasound reports or EMR or symptoms descriptions. This usually forms a multi-tier dependency graph requiring dynamic orchestration based on clinical operation and logic. The static data pipelines, for short, to meeting this kind of demand. For example, if we want to automatically initiating a secondary check when detecting some abnormal symptoms, the static kind of data pipelines or scripts usually cannot be easy to meet this kind of requirement. Second is compliance. In healthcare industry, data pipelines must be audible. Coordinating the tasks across various systems like the HIS, LIS, PACS, RIS demands the end-to-end traceabilities and resilience. For example, trickling image appointment based on lab result must be both automated and compliant with reliability standards. Airflow's DAG visualization and retry policies are instrumental to meeting this kind of industry requirements. In summary, why we choose Airflows? First is the Python native extensibilities. Python is the default language we use for data. We use Python for data analytics, for machine learning tasks, and Airflow's native support for Python gives the team this ability to work with. Second is the clinical fit. As I mentioned before, complex branching, SLAs, retries, and clear escalation paths can be tailored to fit into different clinical scenarios. In the second part, actually, Huiliang is going to show you how we use external task sensor to enforce clinical wording across different systems. Finally, flexible deployment. Teams can make quick code changes to the workflows, and then without much kind of effort, can quickly deploy to production. And with the monitoring in place, if anything goes wrong, the system can automatically roll back to the last stable working version. In short, Airflow balances the power and flexibility and governance very well, which is critical for the healthcare industry. Now, I would like to pass to Huiliang to introduce the specific use case, how we use Airflow to address healthcare industry's specific use cases.
Hi everyone, I'm Huiliang Zhang from I-Kang Healthcare Group. Today, I will be supporting FHIR in delivering this presentation. The following part will be I-Kang's tailored enhancement for healthcare use cases. Now look at our first scenario, cross-system event-driven scheduling. To enable this kind of orchestration across different systems, we implemented a flexible event-driven DAGs. The key here is using operators like the external task sensor and the trigger dagger run operator. Let me give you a concrete example like this. Triggering radiology. This is a crucial step in our physical examination process, but it doesn't happen in isolation. It usually depends on the patient status from the checkup systems and their labor results. So here's how it works. When our radiology scheduling DAG is activated, it uses an external task sensor to keep an eye on two key tasks. It's waiting for task 1 in DAG 1 from the healthy checkup system and task 2 in DAG 2 from the lab system. After both of these tasks are successfully completed, the system moved forward to actually trigger signal radiology workflows. The design effectively ensures orderly data orchestration across our multiple pipelines. Now, let's dive into our second case study, health checkup report scheduling. This is another prime example of how we handle business critical task scheduling. Generating a final health report is actually quite a complex journey. It involves multiple systems working together, and it typically goes through 4 main stages. The process kicks off automatically once a patient finishes their exam, and it initiates the process and adopts a main DAG and a sub-DAG model. So here's how our pipelines works. The main DAG first passes along the patient ID, and think of it as a first button in our relay race. Now, at the same time, it kicks off 2 tasks in parallel. One is the basic healthy advice DAG. named trigger basic check. You can see it right here in the middle of the slide. The other called trigger radiology result. Just below it, handling the imaging results. Once both of these tasks are completed, the system automatically triggers AI advanced DAG. This AI smartly synthesizes all the results from the previous steps. Finally, we have the doctor review sub-DAG tab in to generate the final report. Throughout this whole process, the main DAG acts as a central conductor. It uses operators like the trig DAG run operator to study the sub-DAGs and keeps an eye on their status. So, what makes this design so effective? It allows for fully automatic parallel processing across our integrated systems. This means reports are delivered much faster and we maintain strict data integrity through built-in validation, alerts, and audit trails. Now let's turn to our second best practice. Visual workflow orchestration for clinic teams. This is all about making complex processes crystal clear for everyone involved. Picture like campaign canvas in the middle. It helps us launch target making for users identified as overweighted in their last medical exam. But the true intelligence keeps in as that the subsequent operational activities are dynamically optimized based on real-time event collection, which significantly boosts our conversion rates. So how does it work? As you can see in the diagram, each color takes as a part of story. Purple nodes are the triggering nodes. They are used to select the right target audience. Yellow nodes act as the workflow control nodes, check if the specific conditions are met, like whether someone has enjoyed a weight loss program or if a text message has been set up successfully. Green nodes are the delivery nodes. In this case, they are responsible for sending out a short message about the relevant health products. Red nodes are our stop nodes, significantly the end of a process. Here is the clever part. The entire scaling of these tasks is seamlessly handled by Airflow in the background. The beauty of this view design is that our clinical teams can focus entirely on the workflow logic without needing to worry about the underlying technical details. To really see how all the pieces connect and drive results, let's dive into the technical design on the next slide. So how do we make powerful data orchestration accessible to our medical teams? The answer is our low-code visual interface built directly on top of the Airflow. Think of it like this. Instead of writing complex code, our clinic operation staff can now design complex diagnostic flows will use a simple drag and drop canvas. They are visually built a sequence, like triggering an event, calling API, setting up a conditional branch, or even creating loops. And the system automatically generates the underlying Airflow DAG code for them. This approach allows our operations team to rapidly translate clinical protocols into automatic actionable workflows. This not only slashes the time need to launch new services, but also enhance the constancy of care and ultimately patient outcomes. Now let's peel back the curtain and see how this all comes together. The architecture can be broken down into 4 well-known layers. I will walk you through this from the bottom up. First, the visual front end. This is a drag and drop canvas where users build their workflows. It provides all the building triggerings, deliveries, workflow controls, and branches, etc. Next, the workflow creating service. The service takes the user's visual design and translate it into a structured blueprint, which is stored in the database as a JSON string. Then the DAG generator. This is the engine in the back end. It reads all the JSON blueprint, interprets it, and converts it into the ready-to-run Python code that Airflow understands. Finally, committing it to the production environment. And finally, Airflow schedule. Once deployed, the Airflow schedule takes over, reliably scheduling all the DAGs according to their predefined schedules. In essence, we have created a seamless bridge from a user-friendly visual tool to the robust execution power of Airflow. So, how do we handle the complexity of unstructured clinical test data? At iKang, we have seamlessly embedded a real-time NLP, that's natural language processing, pre-processing right into our Airflow pipelines. But we didn't stop there. We went a step further by integrating a powerful LLM, that is a large language model based multiple engines system, to actively assist in diagnostic design making. Let me walk you through how this works in practice. First, tackling raw data. To address the challenge of data fusion, our system uses a built-in NLP algorithm. Think of this as a real-time feature extraction engine that works directly on medical tests. This ensures that critical information is processed efficiently and ready to the next steps without delay. Next, enable intelligent decision-making. We empower the processes with a LLM-based multi-engine system. The key point is that its reasoning process directly supports the diagnostic workflow. This significantly boosts the accuracy and reliability of decisions in critical clinical scenarios. Then, ensuring smart collaboration through a dynamic routing mechanism, we achieve a combined innovation of different algorithm engines. This flexibility allows to optimize the teamwork among agents, dramatically improve the system's overall efficiency. And finally, verifying the output, we automatically verify the multiple model results through consistency checks. The crucial steps act as a quality control gate, ensuring the validity and consistency of the final output. This lays a solid foundation for trustworthy application in real-world professional settings. So how do we ensure the highest quality for the vast amount of data flowing through our system? We employed a multiple engine LLM framework specifically for intelligent decision making. Think of it as a team of specialized AI engines work together to formulate data quality rules and perform comprehensive checks across every layer of our data warehouse. Let me give you a concrete example of how this works in a medical context. We have specialized workflow engines that can autonomously design data quality control rules. They then involve LLMs to make intelligent quality control decisions on critical data, like examination item results and image results. This involves two key capabilities. First, extracting feature data from the unstructured text. For instance, pulling out specific details, like the location of the size of the nodules from descriptive reports such as abdominal on ultrasound results. Second, applying AI algorithms to analyze the imaging photos directly. A prime example is analyze long CT images to extract detailed information about nodules, their types, morphology, size, and dynamic features. Meanwhile, data quality control rules are designed to make quality control decisions on the results, conduct reviews of datasets with discrepancies in data quality assessment, optimize the data pipelines, and enhance the overall data standards of the data. Next, Roy will continue to deliver the final part of the speech. Thank you.
This is our last part of our presentation. So far, you already see how we use the Airflow. As you can tell, Airflow plays a pretty critical role in ICANN's data tech stack and actually helps the industry for better innovation. By combining the domain-specific customization with Airflow's open-source extensibilities, ICANN has actually locked the following capabilities. First is faster turnaround. Through the workflows automation, we achieved faster diagnostic turnaround. Meanwhile, we actually also improved the service quality by having several workflows to monitoring the service quality metrics. We are not only have the services faster, but also have better service qualities. Third, as a second part to show, Airflow helps us to streamline various systems coordinations, like the demo Huiliang just showed. From the lab result, anomaly detection, to the imaging appointment, finally show the result in the EMR. Airflow help us to coordinate the complex system coordination very well. Finally, Airflow help us to make this scalable and compliant and also observable to be aligned with healthcare regulatory standards. In this presentation, we show you how we leverage Airflow, use it as the modern data orchestration framework to help transform healthcare business at scale. We believe there might be some other teams also handling sensitive and multimodal data. So we would like to compare our usage patterns with you and hear from you, your team, how you are handling similar problems. We are also looking forward to contribute what we build with Airflow back to the open source communities. That's all from our presentation.